Lesson 4. Quicksort. The quicksort algorithm is performed by a repeated application of what we will call the partition step, which divides an array into two sets. To explain the partition step, we begin with an unsorted array. Then we select one of the elements of the array to be the pivot. Ideally, the pivot should be the middle value of the array. However, finding this requires too much time, so we will use a faster method and hope for a reasonably good result. For our code implementation, we will simply select a random element for our pivot. In this example, we assume that the element 34 is selected as the pivot. Once the pivot is chosen, we use it to partition the array into two sets, one with the elements above the pivot and one with the elements below the pivot. We begin partitioning the array with two selectors at the first and last elements, shown here in gray. The first selector is moved forward until it reaches an element that is larger than or equal to the pivot. Then we move the second selector backward until it reaches an element that is smaller than or equal to the pivot. Once the first selector has an element that is larger than or equal to the pivot, and the second selector has an element that is smaller than or equal to the pivot, we swap the values. Then we continue selecting the next element that is larger than or equal to the pivot with the first selector, and the next element that is smaller than or equal to the pivot with the second selector. Then we swap those and continue this process until both selectors point to the same element, which will always be the pivot. At this point, the pivot is in the correct location, and the array is partitioned into the elements that are less than the pivot and the elements that are greater than the pivot. This finishes the partition step. The full quicksort algorithm is performed as a series of partition steps, which we will describe next. A C++ implementation of the algorithm is available on our lesson page at zoax.net. We begin the algorithm with an array that we want to sort. First, we apply the partition step to divide the array into two partitions. The selected pivot is 19, so we color it white to show it. At this stage, we have two unsorted partitions of 4 elements each on each side of the pivot. Next, we partition each of these sets. Here, the two new pivots 5 and 23 are shown in white, and the old pivot 19 in gray. After partitioning these two sets, we have a partition containing the elements 2 and 3, a partition containing the element 14, a partition between the elements 19 and 23 which contains no elements, and a partition of the elements 35, 43, and 24. We do not need to partition the sets of size 0 or 1 since they are already sorted. This leaves us with the partition containing 2 and 3 and the partition containing 35, 43, and 24. We apply the partition step to these two sets. In this last step, the pivot 3 is selected in the first set and the pivot 35 in the second set. After we partition these sets, the remaining sets all contain 0 elements or 1 element and are therefore sorted. So we are done. Here's the pseudocode for quicksort. We have a function called partition, which takes the array to be sorted and its size as arguments. If the array has less than 2 elements, it is already sorted, so we just return. Otherwise, we randomly select the pivot element from the array. Then we set a lower and upper index to the least and greatest indices in the array. Next, we have the while loop that runs until the upper and lower indices are equal. Inside this while loop, the lower index skips over elements that are smaller than the pivot, and the upper index skips over elements that are larger than the pivot. Whenever L index is an element that is greater than or equal to the pivot, and U index is an element that is less than or equal to the pivot, we swap the elements at these indices. When L equals U, the array is partitioned, and we call partition on each of the new partitions recursively. This recursion eventually sorts the entire array.